Section: Introduction. In this section, we delve into the exploration of uncertainty quantification in language models, LLMs. We identify two main types of uncertainty: epistemic and aleatoric. Epistemic uncertainty arises from a lack of knowledge about the ground truth, while aleatoric uncertainty stems from inherent randomness in the prediction process. Our goal is to distinguish between these uncertainties and develop methods to effectively handle situations where there are multiple valid responses to a query. We observe that if multiple responses to the same query are truly independent, the joint distribution of these responses should be a product distribution. By iteratively prompting an LM for responses based on previous outputs, we can assess the level of epistemic uncertainty. Through our iterative prompting approach, we make several key contributions. 1. We introduce an information-theoretic metric to quantify epistemic uncertainty in LMs, which measures the disparity between the model's distribution of responses and the actual ground truth. 2. We establish a computable lower bound for this metric, which is akin to mutual information of the LM's joint distribution over responses. 3. We propose an algorithm for detecting hallucinated responses by setting a threshold based on the mutual information estimator. 4. We demonstrate the effectiveness of our method on various question-answering datasets, showing superior performance compared to baseline methods. Additionally, we investigate how the LM's output can be influenced by iterative prompting, particularly focusing on a single self-attention head. We find that the prompt composition plays a crucial role in determining the model's response, shedding light on the mechanism behind response generation in LMs. Section Summary. In this section, we delve into the concept of uncertainty quantification in language models, LLMs, focusing on distinguishing between epistemic uncertainty, stemming from lack of knowledge about ground truth, and aleatoric uncertainty, arising from irreducible randomness in predictions. Our approach involves decoupling these uncertainties to effectively handle multi-response queries, utilizing an iterative prompting procedure to measure how close an LLM's output is to the ground truth by assessing the independence of multiple responses to the same query. Through this method, we derive an information-theoretic metric of epistemic uncertainty, propose a computable lower bound using mutual information, and develop an algorithm for hallucination detection based on this metric, showcasing improved performance compared to baseline methods on various question-answering benchmarks. Section: Notation. In this section, we will explain some fundamental concepts that are used in the paper. We use n to represent the set of natural numbers and r for the set of real numbers. When we talk about a measurable set z, we refer to the set of distributions that are supported on z as m_1, z. For any positive integer k, we denote the set k as the numbers from 1 to k. Now, let's discuss conditional distributions and prompting. We define X as the space of finite text sequences, where X is a subset of sequences formed by symbols from a finite alphabet sigma. We consider a family of conditional distributions P, which assigns probabilities to text sequences given a prompt. The ground truth conditional probability distribution over text sequences is denoted as P, and the learned language model is denoted as Q. Moving on to information-theoretic notions, if we have distributions mu and mu, supported on a set Z, we can calculate the entropy of a distribution as the sum of the probability of each element times the logarithm of the inverse of its probability. The Kullback-Leibler divergence between two distributions is defined as the sum of the probabilities of elements multiplied by the logarithm of the ratio of the probabilities in the two distributions. We also define the marginal distribution of a specific coordinate and the mutual information of a distribution. Next, we explore probability amplification by iteratively prompting. By repeating incorrect responses in a prompt multiple times, we can observe significant effects on the output of a language model. The probability of the correct response can be maintained even with repetitions of incorrect information. We provide examples to illustrate this phenomenon. Furthermore, we compare in-context learning with in-weight learning in a language model. We discuss the sensitivity of the model's response to additional in-context information and how it can impact the model's output. We explain the concept of an idealized attention mechanism and how it influences the model's predictions based on the input data. Section Summary. In this section, we introduce basic definitions used in the paper. We define sets for natural and real numbers, distributions supported on measurable sets, and the notation for positive integers. Moving on, we present information-theoretic concepts such as entropy, KL divergence, marginal distributions, product distributions, and mutual information. We then explore the impact of repeating responses in prompts on language models. By incorporating incorrect responses multiple times, we observe changes in the model's behavior, affecting the probability of correct responses. This phenomenon is illustrated through examples showing how the probability of correct answers can decrease with increased repetitions of incorrect information. Section: Metric of epistemic uncertainty and its estimation. In this section, we applied iterative prompting to estimate the epistemic uncertainty of a language model when responding to a query. By observing different behavior patterns in prompting, we can distinguish between high aleatoric uncertainty and high epistemic uncertainty. We then used our new uncertainty metric to create a score-based hallucination detection algorithm. We assumed that multiple responses to the same question, drawn according to the ground truth, are independent of each other. This assumption relies heavily on how we construct prompts. Without including previous responses in the prompt, this independence assumption would not hold. For example, if previous responses were partial answers, like steps in an algorithm or parts of a story, the current response might depend on the previous ones. We introduced the concept of a pseudo-joint distribution, derived from the language model, representing the distribution of responses given a query. Sampling from this pseudo-joint distribution involves a chain rule-like procedure. To measure epistemic uncertainty, we quantify how well the estimated pseudo-joint distribution approximates the ground truth using the Kullback-Leibler divergence. This metric helps us determine if the language model generates sequences that are unlikely in normal language usage. We aim to estimate the hallucination metric, which indicates how much the language model deviates from the ground truth. Under a certain assumption, we can establish a lower bound for the Kullback-Leibler divergence, which depends only on the pseudo-joint distribution derived from the language model. This lower bound is applicable for decision-making and provides a measure of epistemic uncertainty that is computable based solely on the language model's distribution. Additionally, we discuss the query conditional excess risk, which involves controlling errors in learning algorithms, a more challenging task than estimating epistemic uncertainty. Section Summary. In this section, we apply iterative prompting to estimate the epistemic uncertainty of a language model when responding to queries. By leveraging different behavior patterns observed in prompting, we distinguish between high aleatoric uncertainty and high epistemic uncertainty modes. Our new uncertainty metric is used to develop a score-based hallucination detection algorithm, based on the assumption of ground truth independence in responses to the same query. Section: A computable lower bound on epistemic uncertainty. In this section, we provide a computable lower bound on epistemic uncertainty. The lower bound is determined by the mutual information, which measures the uncertainty in our knowledge. However, calculating the mutual information involves evaluating a distribution on its entire range, which can be infinite in practice. Since it's impractical to observe probabilities for all possible outcomes under the distribution, we use a finite sample instead. By replacing the distribution with an empirical one based on a finite sample, we can control the error introduced by this approximation. To estimate the mutual information, we utilize a specific method outlined in the algorithm. This algorithm is designed for a general joint distribution, denoted as mu, although our main interest lies in the distribution y(q). The algorithm constructs an estimator by considering unique elements in the sample and not accounting for duplicate entries. By adding certain terms in the estimator, we ensure that the total probability of missing observations is taken into consideration, thereby bounding the estimation error. The introduction of a parameter, gamma, in the estimator helps us rigorously limit the error in estimating the mutual information. We establish a non-asymptotic bound on the estimation error, which relies on the estimator, the expected missing mass, and the size of the sample. This bound guarantees a certain level of accuracy in our estimation with high probability. Furthermore, we discuss different scenarios for estimating the mutual information. In one scenario, we adopt a pessimistic approach that assumes limited information in the samples, suitable for cases where the distribution is spread out uniformly. In contrast, an optimistic scenario considers a small effective support for the distribution, leading to a more efficient estimation process. By analyzing empirical data, we observe that in practical applications, the effective support size is often small, resulting in a significant reduction in the estimation error. We also explore conditions under which the estimator converges to the true mutual information. The rate of estimation error is primarily influenced by the expected missing mass, which tends to decrease as the parameter k increases. Despite potentially slow decay rates in general cases, for distributions with specific properties like heavy tails, the expected missing mass can diminish rapidly. In conclusion, our analysis demonstrates that the expected missing mass is typically small, especially in scenarios where the distribution follows a ZIF distribution. By leveraging concentration inequalities and repetitive sampling techniques, we can accurately estimate the expected missing mass, leading to precise estimations of the mutual information in practical applications. Section Summary. In this section, we present a computable lower bound on epistemic uncertainty using mutual information. To estimate the mutual information, we replace the distribution with a finite support empirical distribution, controlling the error induced by this approximation. By considering missing mass and sample size, we derive non-asymptotic bounds on the estimation error, showing that the expected missing mass can converge to zero, especially in scenarios like ZIF distributions where the expected missing mass is significantly smaller. Section: Score-based hallucination tests. In this section, we explore score-based hallucination tests. We define a score, I_k, gamma, x, which represents our confidence in the language model, LLM, generating accurate responses for a given query x. This score helps us decide whether the LLM is hallucinating or providing a valid response. By setting a threshold based on this score, we can design policies for abstaining from responding when hallucination is detected. To detect hallucinations effectively, we adjust the threshold through calibration on a separate dataset with known ground truth information. This calibration process helps us fine-tune the threshold parameter, lambda, for a specific task. Our abstention policy abstains from making predictions when the uncertainty in the response is high, as indicated by the estimated lower bound on epistemic uncertainty. In our experiments, we compare different scoring functions, such as the probability of the greedy response, the response entropy estimate, and our proposed mutual information score. We evaluate these methods on various question-answering tasks using different datasets. We use a Gemini 1.0 Pro model for generating outputs and scores. The datasets include subsets from Trivia QA, Ambig QA, and a multi-label dataset based on WordNet. We analyze the performance of different scoring methods for detecting hallucinations on the datasets. Our proposed method shows promising results compared to baseline methods like the probability of the greedy response and semantic entropy method. The experiments demonstrate that our method performs well on single-label queries, while also being effective on multi-label queries with higher entropy. By combining datasets with diverse query types, we further validate the effectiveness of our proposed method in handling varied prediction scenarios. To showcase the improved abstention capabilities of our method, we conduct experiments to compare its performance with the semantic entropy method on datasets with diverse outputs. The results highlight the robustness of our method in handling high-entropy queries compared to the baseline method. Through calibration and threshold optimization, Our proposed method shows superior performance in abstaining from making predictions on challenging datasets with mixed query types.